Okay, so what we're going to be looking at today is finite difference approximations. Okay, so finite difference method, these are built on what we call finite difference approximations. What they do is they solve PDEs by approximating the solution at discrete points in the domain. So remember last week we spoke about, okay, the domain are the set of all values of the independent variables for which the PDE exists. So for example, if you had x as your domain, i.e. a line in space, what we do with finite difference methods is you take your 1D domain and you split it up into lots of points. And what you do is you approximate the solution of the PDE at those discrete points. So when we're dealing with any numerical methods, you're not solving across all of the domain. Okay, it's not what we call continuous solution. It's a discrete solution, so you only get a finite set of points where we calculate the solution. Finite differences are approximations of partial derivatives. So as we saw last week, our PDEs are built on partial derivatives of our function u. Now u is what we're trying to find. Partial differential equations are an equation in terms of the partial derivatives of u. Okay, so the finite difference approximations to the partial derivatives, and we replace any derivative in our PDE with a finite difference approximation. Okay, so instead of writing it in terms of calculus, in terms of a derivative, we're writing it in terms of an algebraic equation. And the solution to that algebraic equation is therefore an approximation of the solution to our PDE. Okay, so in general, to summarize, finite difference methods take a differential equation, turns it into an algebraic equation, we solve that algebraic equation, therefore we have the solution or an approximation of the solution to the PDE. Okay, you may have seen this series before. No doubt if you're doing the ODE unit as well, you'll see it a lot. This is the well-known Taylor series, and this is the basis of most, I was going to say all numerical methods, but most numerical methods are derived in part from the Taylor series. Series is an infinite series, and it allows us to write down a function as a product of its derivatives. Okay, so here's the Taylor series. There are a couple of different representations of the Taylor series. This is one I favour. So we have our function u, and x is our variable of u. H is what's called a step length. So I mentioned in the previous slide, we look at discrete points in our domain. But h is a distance between two successive points. Okay, so how far are our points apart is our number h. Okay, in the Taylor series, we can express this as a summation of u and the derivatives of u. Okay, so I've got ux plus h times the first order derivative plus h squared over 2 times the second order derivative plus h3 over 3 factorial, which is 6, times the third derivative, etc., etc. We can go on forever. We can go on for an infinite number of terms. So we have this summation. Okay, so n equals 0 to infinity. N is the power of 2, and it's also the order of the derivative. Okay, so you can see there's a pattern there. H to the power of 3 divided by, well, 6 is 3 factorial, multiplied by the third order derivative. And so we got an infinite sum. Unfortunately, with infinite sums, we can't calculate that. We can't, because we'll be here until the end of time trying to calculate this. So in a minute, what I'm going to talk about is the idea of truncating the Taylor series. This is sort of known as the forward Taylor series because you're adding h to x. So you're going forward along your domain. Well, if we replace h with minus h, we go backwards along our domain. we have what's called a backwards Taylor series. Very, very similar to the forward Taylor series, except for where you've got h, we replace it with minus h. Now, when we've got an even power of h, even power of a negative is a positive. Okay, so our sign here for any, I should say 2, our sign here for any even power is positive. So what you end up with is, with the backwards Taylor series, you end up with plus, minus, etc. Okay, so we can write this using this neat little trick, minus 1 to the power n. When n is odd, this is minus 1. When n is even, this is plus 1. So that's the backwards Taylor series and the forward Taylor series. Okay, I mentioned, but we can't sum to infinity. We can't sum to an infinite number of terms. Okay, so therefore we have to do what we call truncate. So after a few terms, and depending on how accurate we want our solutions to be, depends on how many terms we take. Okay, we say, okay, we're not going to bother anything past. We're going to sort of draw a line and say, right, anything after this, we're not going to bother with. Now that's okay. The reason it's okay is because of the denominator of this term here. H to the power n over n factorial. Doesn't matter what h is, pretty much. The n factorial soon becomes very, very large. So if we consider it with a fairly what is considered a large step length, which is 10th. Okay, after the 0th term, we've got h to the power 0 over 0 factorial. Remember, 0 factorial is 1. We have 1. After the first term, we have 0.1. Second term, we multiply by 0.005. Get up to the third term, and we're already into the tens of thousands. Okay, in the fifth term, we're in the billions. And we've got a very, very small number here. So after only 6 terms, but the fifth order term, we're multiplying our derivative by a very, very small number. So there's no point going further than that because we're looking at our values we're looking at are very, very small. So when we truncate the Taylor series, this is what we mean. Okay, we don't bother going to a massive amount of terms. We normally go to about 4th order at most. In general, though, the more terms we sum to, the more accurate your approximation. But obviously, the more work you're doing. Between how accurate you want your approximation to be and the amount of work you can do. Okay, so I'm just going to have a look at a Taylor series expansion of e to the x. Okay, just to show you, as the more terms you sum to, the better your approximation is. Okay, 0th order. Okay, our Taylor series is ux. Okay, if x is 0, I've said a is 0 here. So it's a special series known as Maclaurin series. So a 0th order approximation of e to the x is e to the 0. Okay, so that's just 1. Anything to the power 0 is 1. Or the exponential function evaluated at 0 is 1. First order, okay, the Taylor series was ux plus h times the derivative of ux. Well, here what we're going to do is we're going to say, okay, h is going to be 1. Okay, x is 0, h is 1. Or a is 0, sorry. So we have our 0th order term, and this is our first order term. The derivative of e to the x is just e to the x. And so that's x and e to the 0. So that's x 1 plus x. Second order. So we have our first order. That's the same. So that's our 1 plus x. Plus that term there. 1 over 2 factorial times x squared. Third order. Again, we take our second order solution and just add on that third order term. Okay, so the higher order you go, the more terms you have in our series expansion. Okay, if we go to nth order, you can see there's a pattern here. The pattern is x to the power n divided by n factorial. That's a series expansion of e to the x. So what does this mean in terms of our accuracy? Well, here's a set of graphs in your notes. The red line is e to the x, about the point a equals 0. So the red line is what we're trying to approximate. That dashed blue line, that's our approximation. So at 0 order, the approximation of ux equals 1. Okay, so that's a horizontal line crossing the vertical axis at 1. It's rubbish. It's absolute rubbish approximation there. We go to first order. Okay, we've got a straight line. This time it has some slope, so it's a linear slope. But at this point, it's not actually that bad. This sort of approximation around here is pretty good, where it crosses the vertical axes. But the further away we get from the vertical axis, you can see we start to get more error. So the first order is all right close by, but it's no good further away. Okay, second order, we've got quadratic now. Okay, so our power of a variable is squared. Okay, so we have a quadratic, a nice sort of cup shape. So it's actually a pretty decent approximation from about here upwards. As you can see, it soon starts to sort of deviate from the red line. Third order, it's starting to get a bit better. Hopefully you're starting to get the idea. The more terms we have in our Taylor series expansion, the closer our approximation is, the dashed blue line from the function we're trying to approximate. Okay, so that's the key with numerical methods. What we want is we want that blue dashed line to be very, very close to the red line. Unfortunately, we can't have our cake and eat it. Okay? The more terms we put in the Taylor series expansion, the better our approximation is, but the more work we have to do. Sometimes there's a trade-off between how much work you've got to do and how accurate you want your results. Okay, so you'll be hearing a lot of things this year about accuracy. A lot of the time, we don't know how accurate our results are. I mentioned last week, very few PDEs have an exact solution. So if we don't have an exact solution, how do we know whether our solution is accurate or not? And the truth is we don't. Okay, we can sort of test or validate against laboratory measurements. But the way we consider accuracy is as we reduce our step length, that h, remember, was a step length, that's the distance between two discrete points in our domain. The smaller that h gets, the more accurate a solution you have, because you're calculating your solution at more and more points. Okay. So as h gets smaller and smaller and smaller, so as it tends to 0, what's happening to our error? Okay, so when we talk about accuracy in numerical methods, we often use this, which is the idea of the behavior of convergence to 0. Okay, so this is often called big O notation. So it's quite an abstract concept. So here we have a definition. F is any function of your step length h. Doesn't really matter what f is. It's just a function. And we say that f is of big O h to the n if this is satisfied. So what does this mean? F of h is a function. As h gets smaller and smaller, as h goes to 0, the value of f of h is also going to go to 0. If the limit as h tends to 0 of f of h over h to the n, if that equals some non-zero positive constant c, then we say that f of h is of order h to the n. That is a very abstract definition. In sort of other words, if we ignore the limit for now, we say, okay, h is something really, really, really small, so we can get rid of the limit. Okay, multiply both sides by h to the n, we get this. So we get f of h is roughly equal to some constant c, that's just some number, times h to the power n. Because this constant is positive, it's some non-zero constant, this means f of h goes to 0 faster than h to the n. Okay, so we're looking at when h goes to 0, so we're reducing h, we're getting smaller and smaller and smaller. our function f of h goes to 0 faster than h to the n. So when we refer to with accuracy, we don't refer to something being how accurate it is. We refer to something being, if I was to reduce the step length h, how much better would my approximation be? So, for example, this is. I'll come back to that slide in a minute. But if we had big OH squared, if we were to reduce our h by 1/2, we reduce our error by 1/4. If we had something big H to the 3, if we reduce our h by 1/2, we reduce our error by 1/8. Okay. So big OH squared, if a method is said to be, and this means order 2, because the power of h is 2 there. If the method is order 2, if we reduce the step length, we get a bit of a better improvement. But if the method is of order 3, and we reduce the step length by the same amount, we get a much better improvement. Okay, so when we talk about error, we don't talk about values, we talk about behavior. Okay, so this big O notation, this is basically how does our method behave as our step length becomes small. Okay, and it has some of these properties. If f of h is of order n, and we were to multiply our function by k, which is just some number, that doesn't change how accurate our method is. So we can multiply a method by a number, doesn't change how accurate it is. Okay, if we had two methods, or two functions, f and g, and f is big O h to the n, and g is big O h to the m, and m is less than n, then we say we use the smaller of the two. Okay, so if you were to take a second order method and add it on to the first order method, your combined method would be first order. You take the worst case scenario. Okay, if you got f of h divided by h, okay, remember f of h is h to the n. Your big O, the power will be n minus 1. That's a very, very useful result, this one. Okay, and there are a few other, these two down here aren't particularly useful. Okay, the point being is big O notation is a behavior. Okay, it's not a specific value. Okay, so we use big O to denote truncation error. So we truncated our Taylor series after, let's say, 4 terms, or in this case, 2 terms, or n terms, for example. So we truncate it after that, and there's going to be other terms which we've missed out. Because we've missed them out, our equal sign here is no longer correct. The left-hand side does not equal the right-hand side. So what we do is we add on our truncation error. So this big O h to the n plus 1, that denotes the errors attributed to ignoring all those additional terms. And I mentioned this. So let's say I was truncating after first order. So let's say I had the first 2 terms, that all of this was ignored. I'd have big O h squared. So by halving my step length, I reduce the truncation error by a factor of 1/4. If I actually was to include that second order term and ignore everything after it, I'd have a truncation error of big O h cubed. So if I was to halve my step length, I'd improve my truncation error by a factor of 1/8. So that's the idea of truncation error. Okay, so I've got an example here. So I'm going to use the Taylor series just to approximate a function, and the function is sine x plus h. Okay, so Taylor series, I have u of x, which in this case u of x is sine x, plus h times the first order derivative. So derivative of sine is cosine, plus h squared over 2 factorial times the second order derivative, so the derivative of cosine is minus sine, which is where that n comes in, etc. Okay, so that's a Taylor series expansion of sine x plus h. Let's have a look at when x is 1 and h is 1. Okay, so first order, so that's only including the first two terms, because that term there is what we call the zeroth term, and that's the first term, that's the term 1. Okay, so first order, okay, if x is 1, h is 1, we're looking at sine of 2. We're trying to approximate sine 2. So we've got sine of 1 plus h, but h is 1, and cosine of x, which is 1. So we've got 1.3818. If I do the second order, I have my first order term plus this term here. So that corresponds to that term there. So minus h squared over 2, well h is 1, so that's just going to be 1 over 2, times the sine of 1, okay, which is 0.9610. Third order, again, we add this term onto our second order solution. So here we've got minus 1 to the power of 3, which is 1 over 3 factorial, which is 6, times cos of 1. Again, add the fourth order term. So this is a rubbish approximation. We get slightly better with second order, slightly better with third order, better still with fourth. If we were character fifth, we get better and better and better. What about if we halve our step length? Okay, so we're still looking at sine of x plus h. Okay, but our h is reduced now. Okay, we're saying, all right, the distance between 2 points is reduced by a half. Okay, so what we're actually approximating is sine of 3 over 2, because 1 plus a half. So in this case, our h is no longer 1, it's a half. Half cos 1. Second order, okay, so we take our first order solution, and in this case, h squared, well, if h is a half, h squared is 1 over 4. Divided by 2, we get the 1 over 8. Okay, so 1.0064. Third order and fourth order. Okay, so we get 0.9974. So as we go more and more terms on our Taylor series, we get a better and better approximation. Okay, and if we do the same, keep halving the step length. So here, I keep halving the step length. This is the exact solution. So this is sine of x plus this number. Okay, remember, we're always dealing in radians. And this column is the first order. Okay, approximation using those h values. That's second order, third order, fourth order. Because we know what the exact number should be, because we're just approximating sine x plus h, what I can do is I can calculate the difference between our approximations and the exact number. And I've taken the absolute value, so I'm ignoring any signs. And here we have our errors. So when h was 1, okay, our first order was very poor, 0.47. It was like 0.47 away. Second order, 0.05 away. Third order, 0.038. Fourth order, 0.0032, etc. So as you go higher and higher the order, that error goes smaller and smaller. As you decrease h, you'll notice the error also decreases. What we can do is we can use, because we've got different values of h, we can approximate what our order of our method was. Let's say I only had that and I didn't know whether they were first, second, third, or fourth order. I can approximate what the error or the order of the error is here. And to do that, well, we can graph it. Okay, so here we have a graph. So this is of h, so that's the one we started on. We started with h equals 1, then we halved h, so half, we halved again, halved again, halved again. So we're reducing h each time. Okay, On the vertical axis, I've got error. So you can see the blue line represents our first order. As we reduce the step length h, our error for our first order comes down quite considerably, and then it starts to come down further and further. So as h reduces, our first order method tends to 0. But the second order is so much better, the red line. Again, as h reduces, that gets closer and closer to 0. That graph in itself is not very useful. Okay. I can't tell the difference much between the black, green, and red lines down here. Okay, it's not useful. But we can do a neat little trick. Remember our definition of big O notation. We had f of h was approximately equal to c h to the n. So instead of saying f of h, I'm saying e of h. So I'm assuming that our error for a particular step length is of order h to the n. I want to find out what that n is. Okay, so what I can do is if I take logs of both sides, okay, I have a linear equation. N is my gradient of that line. It's a linear equation, y equals mx plus c, where n was a gradient. In this case, n is a gradient. So if I calculate the slope of this line, after I've taken logarithms, I can calculate what my order of error was. And you could also plot it on a log-log scale. You all know about log-log scales? So normally a command in MATLAB or in, actually I don't think there's one in Excel, but in MATLAB there's a log-log command. And what this does is it turns the scale of your plot into a log scale. So each of these is times 10 to some power different. Okay, and also on the vertical axis. So it's sort of stretched the scale of it. And you can see that these now are straight lines. I don't know what's happened to that black one now. I think it's just simply come out and printed. It should be a straight line, but it looks slightly wiggly. Okay, so the blue one, which is first order, as your step length decreases, the error tends to get smaller and smaller. But you can see the slope of the blue one is a lot shallower than the slope of the red, which is shallower than the slope of green. The steeper the slope, the more accurate we're getting with smaller, well, when we reduce this step length. And we can calculate or approximate our order there. So for the first order one, my worst error at h equals 1 was 0.47. And when h was an eighth, 0.0125, that was the error. So there's h, 0.062 by the way. So if I take log, the difference between the log of the errors, divided by the difference between the log of the h values, I get 2.037, blah, blah, blah. That is approximately 2, so the truncation error will be big O h to the 2. Do the same with the second order one, you get approximately 3, so it's big O h to the 3, etc. Okay, so I've been rabbiting on for quite a bit. If you turn to page 16, there's what I call a worked example. It's sort of unfinished in your notes. So this is what we're going to have a look at now. I'll try and set up the camera so you can see it. Okay, so the worked example. Estimate the convergence behavior of the truncation errors using first, second, third, and fourth order Taylor series of cos pi over 4 plus h. Okay, that's what I'm trying to approximate. Okay, so Taylor series expansion of cos x plus h. Can anybody tell me what that would be? What would the first term be here? First term in the Taylor series is just ux. So our u in this case is cos. We've got cos x. Then to that we add h times the derivative of that term. So what's the derivative of that term? Minus sine. So we've got minus h sine x. What's the derivative of sine x? Cos x. So we have minus h squared over 2 cos x. And the derivative of minus cos is plus sine. And finally, we have h to the 4 over 4 factorial, which is 24, times cos x and if we put the truncation error in there, so what you do is what's the highest order you included, you go one more than that. And so you go h to the 5. Okay, that was for x's. Okay, if we were to put in x is pi over 4, can any of you tell me what the cosine of pi over 4 is? What's pi over 4 in degrees? 2 pi radians in a circle. Pi over 4 in degrees, 45 degrees. So what we've got is, imagine you've got that. Right angle triangle with side, both two of the shorter sides equal to 1. What's the length of the hypotenuse? Yeah, root 2. So therefore, what is the cosine of that angle there? Cosine's adjacent over hypotenuse. Cosine will be 1 over root 2. What's the sine of pi over 4? Same thing, yeah. So cos pi over 4 is 1 over root 2. I picked pi over 4 just so it would make it easier like this. Okay, so then we got minus h times 1 over root 2 minus h squared times 2 over root 2. That's h cubed over 6 over root 2. H to the power 4 over 24 over root 2. Okay, so if I want a first order approximation, I calculate those two. If I want a second order, I just add that term to my first order. If I want a third order, I add that term. If I wanted a fourth order, I add that term. Okay, what's the exact? Okay, when h is 1, can anybody tell me what cos of pi over 4 plus 1 is? I haven't got a calculator with me, so I'm relying on you guys. Nobody got a calculator? Cos of pi over 4 plus 1? Nobody? Oh,
0.80.
0.80.
0.80.
Should be around 0.2-ish.
Minus 0.2129.
Right, 0.21.
295.
Keep going.
8.
We go 6 decimal places. Okay, so the first order approximation with h as 1 will be 1 over root 2 minus 1 over root 2. Well, I can do that one. 1 over root 2 minus 1 over root 2. 0. Okay, second order. We take our first order and we subtract minus 1 squared over 2 root 2. Which, if I quickly work that out in my head, is about minus 0.353553. I did that in my head, honest. I haven't got them already written down in front of me. Okay, to calculate the third order one, we take our second order and we say plus 1 to the power 3 over 6 root 2. And if you were to do the calculations, you'll get minus 0.23570. I'll show you a quick way of doing this in a minute. Don't worry. And the fourth order, take that number plus 1 to the power 4 over 24 times root 2. And we get minus 0.206239. So that was our exact. That's what we're aiming for. This minus 0.212958. Our first order was rubbish, miles off. Second order, not much of an improvement, but it was. Third order, getting a bit better. Fourth order, getting better still. The reason why actually the fourth order is quite far away from this exact number here is because H1 is quite a large step length. When we talk about step length, we normally talk about H in the terms of hundredths, like 0.01, you normally say. Okay, well, what if we reduce H by 1/2? Okay, this time, cos of pi over 4 plus 1/2. Anybody know what that is?
0.281.
281,510.
540.
Yes. Okay, so first order, we'll have 1 over root 2 minus 1/2 over root 2. So that is 0.353553. Bit of a fluke, by the way. So that's also that. Just a fluke for this time. Okay, second order, so you take that number and we subtract 1/4 divided by 2 root 2. So that would be 1 over 8 root 2 subtracted from that number. This gives you 0.265165. Third order, you take that number, you add 1/2 to the power 3 is 1/8 divided by 6 root 2. Okay, so what's 6 8s 48, so that'd be 1 over 48 root 2 added to that. That's 0.79896. Okay, we take that number, add h to the power 4, well h is 1/2, so that'll be 1/16 divided by 24 root 2. So you start to get small numbers there, so that'll be 0.281738. Okay. Actually not that bad there, 0.2815, here we've got 0.2817. Okay, so we're getting closer. If you were to halve the step length again, so now we've got a step length of 1/4, what would the exact one be? So pi over 4 plus 1/4. Cos of that, I don't know. Anybody know? About that. So if the first order would be 1 over root 2 minus 1/4 divided by root 2, which will get 0.530330. Second order, again, we take that number, we subtract h squared, which is 1/4 squared, so that will be a 16th divided by 2 root 2. That would be 0.50823. Keep going. Anybody know what that exact one should have been? What's the cosine of pi over 4 plus 1/4? Anybody know? Sorry, 0.5? 1.5.
No, 10.
So 5.1.
0.1.
0.13.
183.
183, sorry. Okay. Hopefully you start to get the idea. It might be wrong. I'm going to do it on the computer again in a minute, so don't worry too much about that. Hopefully you're starting to get the idea. There's a reason why I'm getting you to fill out this table. Does anybody know what it is? I'm trying to make it tedious. Okay, well, lecturers by our nature, we shouldn't be trying to make something tedious. The reason why this is slightly tedious is because I want to sort of get you to thinking in terms of more using computers to do this boring work for you. Okay, you're right. You can do it with pen and paper and calculator. It's quite easy, but it's taken us a while to do this. Okay, so what I'm going to do now is show you a little cheat. Well, it's not a cheat. It's using the tools available to us. Anybody guess what tool I'm going to use? Yeah, I thought I'd use something else. Oh, thought you could see that then. Fortunately from this, I'm going to zoom right in. There we go. You can do all this on Excel. So you don't have to go to MATLAB if you don't want. Don't know why you wouldn't, but okay. So we had our values of our h's, which we kept halving them, didn't we, or divide by 2. Okay, so there's our h's, and let's type in our exact or calculate our exact column. So this was equal to cosine of pi. For some reason, when you enter in pi into Excel, you have to put a bracket up, a couple of brackets after. I don't know why, but so pi over 4 plus, and then the h is whatever is stored in A4 in that instance. Okay, so that was our exact solution. Actually, it's not exact because Excel itself is using a truncated series to calculate that, but it's more accurate than what we'll be doing. Okay, so what I'm going to do now is just calculate the first, second, third, and fourth order approximations. So our first order, that was equal to 1 over root 2 plus the h, which is E4 in this case, divided by square root 2. Anybody, are you familiar with this sort of dollar sign here? And what I'm going to do in a minute is I'm going to copy it across. Actually, I'm not going to copy it across. Yes, I don't know. I didn't actually need that dollar sign. So, oh well. If I was to copy it across, that would fix that A column. Okay. Was it minus yet? No, I'm trying to work on 2 different screens here. Go across. It should have been 0, shouldn't it? Oh, happened there. Yeah, it's really, really small on my screens. Yeah, there we go. Okay, so we got an answer of 0, which we wanted to. For the second order, okay, we take our first order solution, and then we subtracted A4 squared divided by 2 times square root 2. Okay, third order, we take our second order, and we add our h cubed divided by 6 times square root 2. And finally, the fourth order. We take our third order and we add h4 over 24 times square root 2. Okay, well, where's me thing? Okay, now I've got all the top 4 done. All I need to do is copy this down and it completes all the values. Okay, I'm not going to, you know, I'm not going to waste my time with the hand calculator when we've got Excel. So as you can see here, this column is your fourth order solution. That's quite close. It's getting actually very close to the exact solution. Okay. Now, how close is it? Let's calculate the errors. So I'm going to create another table just over here. I'll call it errors. Okay, and what I'm going to do is I'm going to calculate the absolute error between each approximation and the exact. Okay, so there's my exact minus the approximation. Okay, so that's the one for the first order. So all I have to do now, if I can just go across, okay, and then copy it down. There we go. So there's my errors. So that's your first, third, and fourth. Okay, so as the h gets smaller, okay, our errors are getting smaller and smaller. But these first order errors are only reducing quadratically, order h squared. Our second order errors are reducing cubically, because they're order h to 3. Third order ones are reducing quartically, and the fourth order ones are quintically. Okay, so it's the power of h is one more than the order. Okay, so if I head back to the document camera, I'm not going to do it by hand because I'm lazy. You can fill out that one there. Okay. Okay, so once we filled out this one, and I'm going to do it on Excel in a minute, we can actually approximate. Okay, what should our n be in the big O notation? Okay, so I'm going to go back to the Excel. Okay. Okay, so what I could do here is for the first order, okay, I'm going to take the log, okay, what's the worst error, which is the one at the top, so the error for h equals 1, and minus the log of h equals 1/16, I think it is. Okay, so what's the difference between the log of that and the log of that? I'm going to divide that between the difference between the log of the h's. So divided by the log of 1, which is there, minus log of that one. And you get 1.8248. Round that to the nearest integer, that's 2. It's never going to be exact, so it's quite a crude analysis, but gives you some idea of, oops. Anybody know what happened there? When I did these ones up here, I didn't put a $sign in front of the A. And then I can go back and copy that one across. So these are my approximation of ends. Okay, so there's 1.84, roughly 2, 3.05, roughly 3, 3.911, roughly 4, 5.04, roughly 5. So what these numbers are is what is the exponent of that function big OH, okay, and that gives it there. So you can see the higher up the order we go, the bigger the exponent, the quicker the error tends to 0. Sorry? Good question. If I just flip back to it always does this. Right. It was this thing here. So n, what you do is you take the log. That is the your error. The h is, or your worst value of the h. That's your error is the best value of the h, divided by log of h minus log of h. Okay. So it's just calculating the slope of a straight line. So that was for that example. And if we go back, you can see that's for this example. So each example's It is not an exact science. This is not exact analysis. It's kind of a bit of a rough guide. Right, for some reason that's gone a bit awry. So. How do I get that off? Okay, for some reason give me a sec. Okay, so that was this analysis. Right, so that's all to do with that. The reason I did that is to try and get you to understand the idea of that big O notation, what happens to the error as h gets smaller. So what we're going to move on to now is looking at finite differences. Okay. Now consider the first order Taylor series expansion. Okay, so that's my 0th order term. There's my first order term, and that's my truncation error. So I've ignored anything after first order. If I rearrange this so that this derivative is the subject, simple algebra, okay, we get this. Okay, so we get ux plus h, which is that thing on the left-hand side, minus ux divided by h. And we also get the truncation error, big OH squared, divided by h. Now we saw earlier, if we divide a function which is big OH squared, you reduce the power of h by 1. So what we get is we get this expression here. Now this, have you seen this before? This is called the first order forward difference approximation. It's first order because the order of the error is h to the power 1. Okay, it's called a forward difference because what we do is we're stepping forward by h in our domain and subtracting two numbers. So we step forward, take that number, subtract ux, divide by h. That gives us an approximation of the first derivative. That's first order accurate. If we did it the same for the backwards Taylor series, we get something very similar. Okay, again, same error. So this is what we call a first order approximation. But this is backwards. We take our value at x, step backwards, take our value of x minus h, subtract them, divide by h, and we get an approximation of that derivative. These are examples of finite difference approximations. Okay, and these are first order. Hopefully you're getting the idea now, but first order is kind of inaccurate. It's rubbish. What if we wanted to increase the order? Okay, so instead of taking a first order Taylor series, what I've done here is I've taken a second order Taylor series. So Taylor series expansion, ignoring any term after third order. I've taken a forward and a backwards one. If I subtract the backwards one, backwards Taylor from the forward Taylor, okay, I get this. So as you notice here, we've eliminated those two terms, and we've eliminated those two terms. But you can see we've still got big OH to the 3. Okay. Rearrange to make the first order derivative the subject, and we get this. Okay. So this steps forward, calculates the value of our u there, steps backwards, calculates the value of u there, finds a difference, divide by 2 times the step length, and we have what we call a second order approximation. So that's a lot better than our 2 first order approximations before. And this is known as a second order central difference. We've sort of going either side of where we want the derivative to be approximated. Okay, so what I've got here, this is some function. Black line is our u. The dashed blue line is the derivative of u at that point, at x. What I want is to approximate that slope of the blue dashed line. The forward difference, what it does, okay, it takes a step forward by h, evaluates the function, and calculates the slope of the line going through those 2 points. Okay, so it's quite rubbish. That's not a very good approximation of that slope. What about the backwards one? Well, this time, instead of going forwards, we take a step backwards. So we use those 2 points to calculate the slope. And again, it's not a great approximation. Central. So central, we go forward and backwards. So we ignore the bit in the middle, take a step forward, take a step backwards, and approximate the slope, and it's a better approximation. Okay, so our central difference, which is second order, is better than our first order differences. Stands to reason. I'm going to explain how to sort of derive these finite differences in a minute in a general sense. But before I do, we often find we encounter mixed derivatives. What I mean by this is, for example, let's say we have the function u partial differentiated with respect to x and partial differentiated with respect to y. In this case, we use this property. Okay, so d2u dx dy, or partial u partial x partial y, we can differentiate with respect to one variable before differentiating with respect to the other. It doesn't matter which way around we do it. So for example, this means we differentiate u with respect to y, and then whatever we have, we then differentiate with respect to x. We'll get the same if we do it the other way around. The same applies for finite differences. So if I wanted a finite difference approximation of this, okay, well, I'm going to take, for example, I'm going to take a first order difference for x. I'm going to use a second order difference for y. Probably wouldn't bother doing that if this is a real case. I'd probably choose both second orders, or maybe higher. But this is just to show an example. Okay, so the first thing I do is I'm going to differentiate with respect to x first. Okay, so this is my finite difference. So I go forward a step in the x direction. Now delta x just means that step length in the x direction, because I've got two variables I need to distinguish the step length. So I step forward with x, y stays the same. This is a function of two variables, I'm not touching y, and minus the value at ux, y. So take a forward step, minus the sort of current value. Divide that by the step length, where that comes from. Each of these is a derivative. So that's the partial derivative with respect to x. Okay, what I have to do for each of those within the square brackets is then apply the finite difference with respect to y. Now I've chosen a central difference formula in the y direction. So this one here, okay, notice I'm not going to touch the x plus delta x, that's going to stay the same, but this y, this second variable, that goes forward and backward. So we go forward in y, backwards in y, divided by 2 delta y. Okay, and we have to do the same for this one here. So I'm not going to touch the x, but I'm going to go forward and backwards in y. Okay, I can combine that. Okay, so if I combine that, that should be a plus. Oh no, yeah, that should be a plus, by the way. I did notice that earlier. Don't know whether it's like that in your notes. Yes. Yeah, this last term here should be plus because we've got a minus of a minus. You see that one there? Okay, this is of order. So here I have this approximation. This is of a double derivative. This is of a mixed derivative, both in the x and y direction. Because I used a first order accurate approximation in the x direction, it's first order accurate in the x direction, but second order accurate in the y direction. That's unusual. Normally you'd pick the same order of accuracy in both directions, but I just did it for an example. Okay, so I've got another worked example. What we're going to do is derive a second order accurate finite difference approximation of this. So in both directions, we're looking at second order.
Did I do that one?
Okay, so what we're going to do, so I'm going to do similar, but this time I'm going to use second order in both directions. Okay, so a second order derivative, ux, okay, because I'm differentiating with respect to x, that y stays fixed. We're not touching it. Okay, so what we have is I have u forward in x, so delta x is that step length in the x direction, and y stays the same, minus a backward step in x, and y stays the same. That's over 2 delta x. Hopefully you're going to be neater on your one than I am here. These are similar for the y direction. Okay, this time x is the one that stays fixed, and we're differentiating in the y direction. So we've got y plus delta y minus y minus delta y. And that's over to delta y. Can you see where that comes from? Is that sort of confusing? So that's the 1D central difference formula, but I've just done it in with a function of 2 variables. Okay, right, so what we have, again, I'm going to go in the x direction first. Yeah, I'm always doing that. Yeah, thanks for pointing that out. I'm always doing that. Okay, so I'm going to differentiate in the x direction first. Okay, so what I'm doing is I'm doing this one here. So I say it's 1 over 2 delta x. That's that bit. Okay, and here I'm going to have this function, but I'm going to have to differentiate this with respect to y afterwards. So I'm just going to put a little y there just to show you that I'm differentiating with respect to y afterwards. Okay, so that's differentiated with respect to x. Then, both of these, I've got to input this central difference for. So this one, remember the x stays the same, so both of my terms here is going to have x plus delta x in it. Sorry about my left-handedness, I'm often doing that sort of thing. Sorry about that. Did I tell you last year, fed back that they said I should get a glass hand? They wanted me to chop my hand off them. Okay, so ux plus delta x, that's the same, but this time we go forward in y. And we subtract, again, ux plus delta x, that remains the same, and we go backwards in y. And that's all over 2 delta y. Okay, so that's the first derivative. now I do the second derivative. Oh, minus. Okay, so I've got u minus x minus delta x. Oh, sorry, that was fine. My fault. Thought I made a mistake. Okay, so essentially I've replaced each of those with its own finite difference approximation. If I combine them all together, well, I've got 2 delta x times 2 delta y. So I've got 1 over 4 delta x delta y. I've got u x plus delta x, y plus delta y, minus u x plus delta x, y minus delta y, minus u x minus delta x, y plus delta y. And this time it's plus. I always get this bit wrong because you've got a negative there, which is multiplied by a negative there. Plus u x minus delta x, y minus delta y. So if you were, not this week, but next week, we'll be looking at what we call stencils. If you were to have a look at what's happening here, and let's say that's in x, and that's in y, that's the point I'm trying to find this mixed derivative at. Okay, I go to these points here. So if that is delta x, and that distance there is delta y. Okay, I've gone to sort of like the 4 corners. I've taken that corner, which is there, minus that corner, plus that corner. Okay, calculate that. 1 divided by 4 times delta x times delta y. That will give me an approximation of that mixed derivative. And that will be second order. So if I put the truncation error, that's second order in both x and y direction. So that's just from combining finite differences. Is that right? Has everyone sort of got that down? Oh, okay, I'll leave it a couple more minutes. Okay, so I'm just going to move on now and just going to look at the last thing we'll be having a look at today. There is a better method or a more general method which we can use to derive these finite differences. And this is called the method of undetermined coefficients. And it's a procedure, and this can be used to sort of derive finite differences. It gets a little bit messy if you have to go to fourth order using the Taylor series as we did before. Okay, so this is the general method, and this is the procedure. So, number of steps. Okay, so let's say I've got a derivative, or I've got a function u, and I want to derive finite difference approximation of its derivatives. Okay, what I do is I first sort of invent a stencil. And this is, by stencil I mean, okay, so what values am I going to use in my approximation? So we saw in the forward difference, we use ux plus h, and we use ux. And in the backwards difference, we use ux and ux minus h. Well, let's say we're going to derive something like a central difference. We use the backwards, one step in the backwards direction, plus ux, plus a step in the forwards direction. Okay, so I write my derivative. You notice it's nth derivative. I haven't decided which one I want to do yet. But I have alpha 1, alpha 2, and alpha 3. These are what we call undetermined coefficients. I don't know what the values of them are yet. That's what I'm going to have to try and find out. And what we do is we replace these two with Taylor series. Okay, ux minus h and ux plus h. We replace them with Taylor series. We factorize out our u's. We factorize out all the u terms, and eventually we'll end up with a linear system of equations in terms of the alphas. Okay, I know this is quite difficult to really sort of comprehend at this moment, but as soon as you see it, an example, it becomes clear. Okay, so we form a system of equations in terms of alpha, solve that system of equations, we've got our alpha values, and therefore we've got our finite difference approximation. Okay, so let's have a look at this example. So here's sort of my basic stencil. I know, but I want to derive a finite difference that uses these values. Okay, so I've chosen to do a second, what have we got there? Second order Taylor series. Okay, so ux minus h, instead of that, I've replaced it by a second order Taylor series. Ux is fine, I don't have to replace that with anything, so that's exact. Again, replace it with the second order Taylor series. Okay, so that's just this step here, this equation with the ux's, etc., replaced by Taylor series. What I then do is factorize out the u values. So factorize out the u terms. So what we have here, first have a look at all the ux's. So here we've got ux, so we've got alpha 1 ux. Here we've got alpha 2 times ux, and here we've got alpha 3 times ux. So if I was to factorize out ux, I'd have alpha 1 plus alpha 2 plus alpha 3. Okay, now do the same but for the first derivative of u. So here, that's my first derivative of u. I've got minus h times alpha 1. Here I haven't got anything, so I ignore it. And here I've got plus h times alpha 3. Okay. I can factorize out the u, the first order derivative, and I can also do the same with h. So I get minus alpha 1, which is that one here, times h times ux, or the derivative of u, and plus alpha 3 times h times the derivative of u. Do the same for the second order derivative. So here I've got alpha 1 times h squared over 2. So I've got alpha 1 times h squared over 2. And here I've got alpha 3 times h squared over 2, which I've got there. So that's what I've ended up with after I've factorized the ux terms out. So what I can now do is I can use this to derive my finite difference. If I wanted an approximation of the first order derivative, I want this term to be 0. I want that term there to be 1, so it'll be 1 times my first order derivative, and I want this term to be 0. if I wanted a second order, an approximation of the second order derivative, I want that term to be 0, I want that term to be 0, and I want a half alpha 1 plus alpha 3 times h to be h squared to be 1. So I want the left-hand side to equal the right-hand side. Okay, so let's say we want to approximate ux. So the way to do that is the first term to go to 0. That means alpha 1 plus alpha 2 plus alpha 3 should be equal to 0. I want the coefficient of u, the first order derivative, to be 1. So I want this, so minus alpha 1 plus alpha 3 times h, I want it to be equal to 1. So the way I do that is set minus alpha 1 plus alpha 3 to be equal to 1 over h. And I want the last term to disappear, I want that to be 0. So alpha 1 plus alpha 3 is 0. Here we've got 3 equations, 3 unknowns, simultaneous equations. It's a linear system, it's quite easy to solve. Okay, so the solution to that is alpha 1 is minus 1 over 2 h. Alpha 2 is equal to 0, and alpha 3 is 1 over 2h. So what we have is my coefficient of x minus h is alpha 1, which is minus 1 over 2h, which is that one. My coefficient of ux is 0, so that's ignored. And the coefficient of ux plus h is 1 over 2h, which is that one. Okay, which is another way of writing that, which is the central difference formula. So I've derived the central difference formula using undetermined coefficients. It's the same one as I derived earlier in a rather easier way, but I just wanted to show you the example. Okay, well, if the earlier derivation was easier, why would I use undetermined coefficients? Well, sometimes, actually, no, sorry, before I get onto that, let's have a look at the second order finite difference approximation, which I've just done. Okay, I've just done all that. Okay. Oh, no, sorry. The second order finite difference approximation using this stencil. So this one's different. This one, that's where I'm trying to find the derivative, but I'm using points x plus 1 forward, and I'm using 1 point forward from that, x plus 2h. That can sometimes happen. If you're close to one end of the domain, you don't have any information from the other side. You can only use information from one side. So we just say this is an anti-symmetric finite difference. Okay, so what's my values of alpha 1, alpha 2, and alpha 3 here? So this is slightly more complicated because I've got x plus 2h. So that's sort of 2 steps along. Okay, well, Taylor series, we replace the h with 2h. So we have ux plus 2h times the first order derivative. Then we had h squared over 2. Okay, so if we had h squared over 2, 2h all squared is 4h squared. 4h squared over 2 is just 2h squared. And that's where that comes from. Okay. So that's the Taylor series stepping twice in the forward direction. Do the same thing again. Okay, so here we replace the ux plus h by the Taylor series, and we replace the ux plus 2h by the Taylor series step twice in forward direction. Again, it's exactly the same. Factorize out. So where are my ux's? I've got alpha 1, alpha 2, and alpha 3. My first order derivatives, I've got 0 alpha 1, but I've got h times alpha 2. Okay, and I've got h times alpha 3. So I've got 2h times alpha 3. And my second order, I've got 0 alpha 1, h squared over 2 times alpha 2, but I've got 2h squared times alpha 3. So I wanted, what do I want to do? First or second order? Okay, let's have a look at first order. So we have this expression down here. If I want to calculate a first order, I want this to be 0, I want alpha 2 plus 2 alpha 3 times h to be 1, and I want this to be 0. Okay, so that gives me my system of equations, three unknowns. Solve that fairly, it can be done fairly simply using algebra. So alpha 1 is minus 3 over 2h, alpha 2 is 2 over h, alpha 3 is minus 2 over h. That gives me this. That's my finite difference approximation of the first order derivative. Okay, it's a second order approximation because of the power of h, but it's only using called nodes from one side. Okay, we haven't gone to the other side, we haven't gone backwards, we've only gone forwards. And that can be used if you're, for example, close to a boundary. If you're close to a boundary and there's nothing existing outside of the domain, we haven't got any information there. So we can use what we call an anti-symmetric difference. Okay, so last thing we're going to be looking at today, worked too hard today. There is a, on page 22, we're just going to go through a worked example. Okay, last thing we worked through today, so don't worry, you flag in. Okay, use the method of undetermined coefficients to derive a symmetric second order. So up to now, I've only derived the first order derivative approximations. What I want to do now is derive a second order approximation of a second order derivative. I think I mentioned last week we use order in two ways. This is a second order derivative, so it's got uxx, but I want a second order accurate approximation. It's yeah, can be confusing when I keep talking about order. One's order of a derivative, one's order of an approximation. Okay. So what I'm after is an expression which gives me an approximation for that. Because I'm going to use a symmetric one, okay, I'm going to choose a node in the backward step. That's a node, current node, and then I'm going to use a node in the forward step. So alpha 1, alpha 2, alpha 3, that's what I'm trying to find out. They are my undetermined coefficients. Okay, so if I insert the Taylor series, okay, so the backwards Taylor, X, trying to remember it now. 2, double X, and I want to go to the third. That one will disappear soon. I'll show you why. Okay, there's, okay. Oh, that should have been a minus, shouldn't it? Some backward step. Should be a minus. Okay, so that's me alpha 1. Alpha 2. You don't have to do anything weird because it's just ux. We know what that is. Alpha 3, it's a forward Taylor. Don't forget to put the truncation error. Okay, because the Taylor series are, I've included terms up to third order, so the truncation error is big OH to the 4. Okay, so my next step is to factorize out the ux and the derivatives of ux. So here, if I take the UX's first, I've got alpha 1 there, I've got alpha 2, and I've got alpha 3. Okay, that's just taking out the UX's to start. Now I'm going to take out the first derivative. So here, I've got minus h times alpha 1. I've got nothing there, and I've got plus h times alpha 3. Second derivative, well, what have I got? I've got h squared over 2 times alpha 1, and I've got h squared over 2 times alpha 3. Okay, I've also got a third order one here. So here we've got minus h cubed over 6 alpha 1, and I've got plus h cubed over 6 alpha 3. So it's alpha 1 over 6 plus alpha 3 over 6 h cubed in that space plus the truncation error. So in this case, I've got 4 equations with 3 unknowns. 2 of those equations are linear combinations of each other. So for example, this one here, minus alpha 1 plus alpha 3, it's just a combination, is exactly the same as that. Well, so if I was to divide that by 6, I'd get that there. So we do have a unique solution. So just write this in here. I'm looking for an approximation of second order derivative. So in that case, I want this coefficient to be 0. And I want this coefficient also to be equal to 0. And I want this one to be equal to 1 over h squared. Okay, so I want all of this just to be equal to 1. Okay, well, why is it 1 over h squared? Well, if I've got h squared there, imagine h squared was the coefficient over here, divided throughout by h squared. Okay, we've got to solve that system now. Quite easy to solve. Okay, so the second equation gives us alpha 1 must be the same as alpha 3. Okay, so if we rearrange the second equation, alpha 1 must be alpha 3. So if we plug that into equation 3, we've got alpha 1 over 2 plus alpha 3 over 2. Well, if they're the same, I've got alpha 1 over 2 plus alpha 1 over 2, which is just alpha 1. We've got alpha 1 equals 1 over h squared. And I've already established that also must equal alpha 3. So I've got alpha 1 and alpha 3. I now need alpha 2, so I need to plug them both into equation 1. So I have 1 over h squared plus alpha 2 plus 1 over h squared equals 0. So therefore, what should alpha 2 equal? Yeah. So alpha 2 must be minus 2 over h squared. So just to remind you, that was what I was trying to find, the alpha 1, alpha 2, alpha 3. If I plug in my values into that one, okay, I have uxx equals the backward step minus 2 lots of the central node plus a forward step, all divided by h squared. Not forgetting the truncation error, order h to the power 4 divided by h squared can be order h squared. Okay. So that's second order accurate. It's a second order accurate approximation of the second order derivative. Have you seen that one before? Fairly common.